Have you ever wondered in amazement just how powerful these monsters of the universe, these black holes, really are? Well, we all know that even light stands no chance in front of these gigantic cosmic objects. Even light itself cannot escape a black hole, no matter how hard it tries. Now, what if I told you that in this universe, there is a black hole that even light cannot escape? Even light itself cannot escape a black hole, no matter how hard it tries. This is a monstrous black hole which is thousands of times bigger and more massive than our sun. This black hole is unbelievably bigger and stranger than anything we can imagine. Of course, today we know a lot about black holes based on mathematical equations and the existence of massive gravitational objects like black holes. From making predictions to actually capturing it in a picture, we have come a long way. But even after all this, the truth is that we still know very little about black holes. Whatever knowledge we have about it is not even equal to the tip of the iceberg. Imagine if this entire universe was filled with these black holes, or what if our universe itself was contained within a black hole? Well, you will get to know such mind-bending facts and knowledge. Today's documentary, so stay tuned till the end because you can't see this inside. This is practically impossible, and that's because it's beyond the capabilities of us humans. Even if we ignore all the practical challenges related to this mission, simply human life is not enough to do this. In case you board a spacecraft and go near a black hole. So as you get closer to it, the gravitational pull exerted by the black hole on your spacecraft will keep increasing. Because of this, time will start moving extremely slowly with respect to you. In such a case, theoretically, you would have to wait for the interior of the black hole, which is practically impossible due to the biology of the body again anyway. Even if you somehow overcome this challenge, still, you will never be able to enter inside a black hole. Suppose a team of scientists sets out towards a black hole aboard a spacecraft, then the first thing they will encounter is actually this accretion disk revolving around the black hole. This is a ring of boiling compressed matter particles which revolves around the black hole at the speed of light. Imagine what would happen when that spacecraft collides with this accretion disk. Of course, it would be a painful end for those curious researchers. However, one theory also suggests that the accretion of electrically charged black holes is constantly cooled by quantum noise. And if that's the case in reality, then that's good news for those researchers who are on this journey to study black holes, because they might be able to pass through such a thing, but their journey will soon come to a dead end. If it's a small black hole, in fact, the immense gravitational pull of a tiny black hole will smash them completely. But at the same time, scientists also say that the effect of gravity in small black holes is relatively less. This means that the journey of our curious researchers can still move towards its destination. But surprisingly, the journey inside such gigantic black holes would truly be like witnessing the entire universe. Yes, believe it, very large black holes almost contain the entire universe within themselves. If we go by the density scale of a black hole, then according to that, our sun would be spread over an area as large as New York City in America. Therefore, our Earth would be only as big as a peanut. For a long time, scientists believed that these black holes would be filled with the galaxies, stars, and planets they had absorbed. But a recent research has changed the scientists' thinking about this. The result of this discovery was that, according to scientists, instead of charged particles, stars, planets, and dust remaining in a compressed state inside a black hole, they constantly keep moving. The space inside a black hole is quite different from the ordinary cosmos. Due to the enormous amount of force inside a black hole, space keeps stretching and deforming. Imagine that inside a black hole, an entire universe exists. Moons, stars, planets, everything. Continuing further research on this, Dr. Nico Dempaplovas analyzes the internal structure of a black hole and the standard model. Well, according to the standard model of cosmology, our universe began with a massive explosion from a concentration of matter. This is the point where the laws of our physics stop working because ultimately everything begins from here. But scientists were puzzled about where this infinite amount of energy actually came from. On this, researcher Dr. Poplawski says that all the matter and energy came out of a black hole. Scientists believe that every black hole has a singularity. On this, researcher Dr. Poplawski says that matter accumulates by going into a compression state. Wagon scientists, in their hypothesis, compared this point of infinite density and gravity present at the center of a black hole to a seed. This seed would be much smaller in size than any known particle, but it would still be divisible, meaning that further breakdown of it would be possible. This seed bursts under excessive compression of matter, and in such a case, the matter inside it drifts off into outer space, and later on, this very matter formed stars, planets and galaxies from particles. Now, it is possible that 13.8 billion years ago, the birth of this universe also happened from just such a seed. That means, right now, we are living inside a black hole, and in the bigger picture, our entire universe is contained within a black hole. Well, this mind-bending theory is directly challenging our entire understanding of the universe so far. Scientists found in their research that after being born inside a black hole in this way, the universe evolved, and then they also saw a way to get out of the black hole. It's kind of like a tree with a common root, in which the tree has two trunks, but their roots are the same. There is a link between black holes and these newly born universes, which is created by wormholes. There is a singularity present between these black holes in which matter is tightly packed with extreme compression as a seed. And when these seeds burst, this matter spreads throughout space, and in this way, a new universe is born. Technically, to put it in fewer words, 1. Black holes are connected to their reversal, that is, white holes, with the help of wormholes, and these white holes release the newly formed universe into space. According to Poplawski, there is a constant expansion of matter inside white holes, and on the other hand, in black holes, matter seeds keep forming, which further give birth to new universes. In support of his hypothesis, he presented both theoretical and experimental evidences. In this sequence, he projected the origination of the universe with the help of two plastic bottles, in which two bottles were joined end to end to display the connection between a black hole and a white hole. It was just like how a wormhole connection is established between a black hole and a white hole, and through it, matter moves from one side to the other. Apart from this experiment, Poplawski talked about everything present in the universe, whether it's planets, stars, or even black holes. He also presented a factual proof related to their rotation, which was scientifically quite rational. He said that everything present in this universe is in motion, whether it's a star, a planet, a galaxy, or even a black hole. Everything is rotating circularly, which is actually the result of the forces happening inside this gigantic principal black hole. Even in a primordial universe, there should be a relative trend of movement. This means that even in outer space, there should be the same rotational parameters as in the black hole from which it was born. In a black hole, the rotation is spiral. This means that the galaxies present in the universe that emerged from it will be inclined in two different directions. Like some galaxies will be twisted from right to left, and some will have rolled exactly in the opposite direction from left to right. This is exactly the same observation made by the astronomer doing research at the University of Michigan. In her astronomical surveys, she found that in a specific area of the universe, galaxies spin to the right, while in the opposite area, the galaxies are spinning to the left. This proves that there is definitely some connection with Poplawski's theory. Another astonishing hypothesis has also emerged, which has been developed by 3 scientists. All 3 of these scientists are associated with the Perimeter Institute for Theoretical Physics. They believe that our universe came from inside a black hole, and that too from an extra dimension, meaning a higher dimension. Until now, we knew that our universe is 3D, meaning it has 3 dimensions. But this theory also talks about the existence of a new dimension, that is, a 4th dimension. Well, this is quite different from the 4th dimension that we imagine in the context of time. Scientists are projecting it as a real-world dimension. They say that our non-observable universe is made up of 3 dimensions. At the same time, the accretion disk circling around the black hole is a 2D entity. So then how can this black hole not be a 4D object? The main idea here is that a star existing in 4D space exploded with a tremendous blast. After that, a 4th dimension black hole was born and matter started accumulating in the accretion disk of this black hole, which even after the flash did not go inside the black hole. The same thing happens with monsters exploding in space, that is, supernovas, when stars suddenly release the matter stored inside them into space. We cannot see the 4th dimensional world. Scientists say that in the 4th dimension, matter behaves in a very different way. It is like a lump with an odd shape. To understand the 4th dimensional world better, scientists created a model. According to this, the gravitational influence of 4D space can cause fluctuations in background radiations. Now, it is possible for us to create a spectral depiction of this radiation, and based on this depiction, we can map the 4D universe through the fluctuations that appear in the radiation. Astronomers around the world are engaged in searching for this new black hole. In 2022, scientists observed how this black hole separates the bright stars in the galaxy Henais 2-10. To make their research even more robust, scientists also created holographic, 3D, and some other types of models of space. Scientists present in Israel recently learned how small microscopic artificial black holes can be created with the help of the rubidium element. Sir Stephen Hawking's Hawking radiation theory suggests that a black hole propagates radiation into space from within itself. Now, let's try to understand the behavior of this actual phenomenon. In the coming time, we will learn about many properties and phenomena related to black holes. But for now, we only know a few things about these mysterious cosmic objects, and that too only in the form of theories. This is about the year 1970 when physicist Stephen Hawking was searching for the answer to a very simple question. Do black holes have a temperature? Believe me, this single question changed some of the fundamental ideas about our universe. The prevailing belief was that the universe is infinite and immortal, that it would never end. But the search for this question took Stephen Hawking into a completely different world, from where we got more information about how black holes work. And the conclusion that emerged was that black holes also radiate energy. This means that even black holes, which absorb everything into themselves, will gradually lose energy. And a time will come when all the black holes in this universe will eventually evaporate and nothing will be left in this universe. Now, you might have a lot of questions in your mind about this conclusion. Like, if the energy that black holes are radiating should remain, but wait, how can black holes even radiate energy? Because what we all know about black holes is that their gravitational field is so strong that not just anything, even light can't escape from them. So then how can radiation come out? By the way, that radiation is called thermal radiation or Hawking radiation. Apart from this, you must have seen high energy jets coming out of black holes in many places. We also call them relativistic jets. That first famous picture of the M87 supermassive black hole, in which these energetic jets are clearly visible to us. So how are all these things coming out of a black hole after all? Anyway, a black hole is a mysterious and weird place. So is our science falling apart there? Otherwise, how can anything come out of a black hole? So first of all, we need to understand the black hole. After that, all your doubts will be cleared. So let's first talk about the black hole, because the root of all the confusion is hidden here. So simply, if we try to visualize what a black hole actually is, so first of all, let's assume that if space is empty, if there is nothing in space, then the fabric of space will be completely flat. If we place a massive object in space, there will be a curvature in space. The greater the mass of the object, the greater the curvature in space. That means there is a direct connection between mass and curvature, and the vice versa is also true. If there is more curvature in space, it means there is a massive body there. If the curvature is less, then the object's mass is less, and if there is no curvature at all, then the object is also massless. Now we have understood the concept of space, its curvature and mass. You can think of it like a crater or a big pit in real life. Suppose you are standing at the edge of a pit. and by chance, if your foot slips, you will roll towards the center of that pit. This pull in space-time is called gravity. The greater the curvature, the stronger the intensity of gravity will be. Now suppose you have rolled to the very center of the pit. This means you are at the center of the curvature. That means you have landed on a massive body. But now, if you want to get out of that pit, that is, if you want to escape from a massive body, you have to get out of its massive gravity. So we will need to apply a specific amount of energy, and that energy is what we call escape energy, escape velocity, or escape speed. After understanding this much, you can imagine a black hole better. Now suppose you place so much mass at one point in space that the curvature it created in space, meaning the pit it formed, is so deep that even the fastest object in the universe, that is light, cannot escape from it. In other words, even light does not have enough energy to get out of that curvature. Now we all know that the speed of light is the ultimate cosmic speed limit. That means any particle that has mass cannot achieve this speed, and those particles that are massless can only go up to the speed of light. This means that nothing can get out of the curvature created in space. So understand that a black hole has formed there whose escape velocity is much greater than the speed of light, but even a black hole has its own limit. Let's understand this with our pit analogy as well. As long as you are far from that pit, you are completely safe. But as soon as you enter a critical region where you slip and start falling into that pit, you just keep falling. That's called the event horizon. If you fall into this region even once, then no matter what you do, you will keep falling inside the black hole and eventually stop at the singularity. Singularity is a point where all the mass of the black hole is concentrated. If you want to know more about this, you can watch our video. You will find the link in the I button above and in the description box below. Any objects outside the event horizon can either escape the gravity of the black hole or fall into the black hole. That depends on their properties. Now from here, we know that any object that crosses the event horizon can never come back. So then how is matter and radiation released from a black hole? For this, imagine yourself as a particle, which is obviously outside the black hole's event horizon, because if you are near the black hole, its gravity will place you in an elliptical orbit. The closer you get to the black hole, the more your speed will increase. As long as you don't cross the event horizon, you won't fall into the black hole. Now, there are many particles like you orbiting the black hole, and you will be interacting with them. The disk formed in the orbit of the black hole is called the accretion disk. The scene of the accretion disk is such that particles are colliding with each other there. Because of friction, the entire disk heats up, and due to this heat, radiation is emitted from the accretion disk. This radiation is called thermal radiation. So actually the radiation is not coming from inside the black hole, but from the matter outside the event horizon. So one confusion gets cleared up here. However, some of the matter in the accretion disk still loses energy and goes inside the event horizon. Because of this, that matter reaches the singularity and the mass of the black hole increases. Besides this, a lot of other things are happening around the black hole as well. In the accretion disk, many charged particles are traveling at the speed of light, and because of their dynamics, a magnetic field is created around the black hole. This magnetic field then accelerates the ionized particles in a special helix shape, and this acceleration happens at the speed of light. And this is what we call relativistic jets. They are very bright and can be seen from very far away in space. There is a galaxy called Centaurus A from whose central black hole these jets are coming out in both directions, while in M87 it has been seen coming out in a single direction. But the important thing to understand here is that these jets and all the energy stored in them do not come from the black hole itself, but rather from the ionized particles orbiting in the accretion disk around it. Even there, nothing is coming out of the black hole, nor can anything come out. The gravity of the black hole accelerates the particles present in the accretion disk outside the event horizon. Where the particles get heated due to friction and collision, they become ionized, which generates electric current and magnetic fields in them, and then this magnetic field accelerates these particles in one direction. This is the simple concept behind relativistic jets. Now let's talk about the most complicated Hawking radiation. It's a bit complicated, but we'll try to understand it in a simple way. So first of all, as we discussed in the beginning, if we remove everything from the fabric of space, even the black hole, that space will become a flat vacuum surface. Now we all know that mass curves the fabric of space, so if we place a black hole at one point, the space there will obviously become curved. An event horizon will form, and the space around it will be governed by the fundamental laws of the universe. Now, the result of this will be that radiation will start emitting from a large region around the black hole, which will be black body radiation, and it will be emitted in all directions. This radiation is what we call Hawking radiation. So now, where is this radiation coming from? Because we have assumed that there is nothing in space except the black hole, so obviously that radiation should be coming from inside the black hole itself. Because here, there is nothing even outside the event horizon. Whatever energy is released in that radiation, it should come from the mass of the black hole itself. But here, our common sense says that nothing can come out of a black hole. So how can Hawking radiation come out, and how can it be proven? If we look at Einstein's famous equation, E equals mass times the speed of light squared, here we can say that with each quantum of energy of Hawking radiation, that is, each packet of energy, E amount of energy is released, so the black hole will lose M amount of mass. But how will this happen? What will be the mechanism of this whole process? Let's find out. The very first and most common simple explanation was not given by Hawking, but it couldn't really satisfy the scientists. But it gave us a new way to visualize energy, so this explanation goes something like this. When space is empty, the energy present in it is called zero-point energy, whose value is non-zero and positive. Now, even though space is empty, meaning it's vacant, from the perspective of energy, we can't treat it as empty. We need something there that can occupy that energy or neutralize it, because the energy in space is obviously already positive. And when you combine this fact with the Heisenberg uncertainty principle, a concept emerges in front of you. What happens is that in that empty space, pairs of matter and antimatter keep coming into existence continuously. They exist for a very short time and then annihilate each other, making the space empty again. This process keeps happening everywhere in space on a massive scale. Now you can assume that the same process must be happening at the event horizon of a black hole. Suddenly, two particles emerged from empty space, one matter and the other antimatter. Understand it like this: if one is a particle, the other is an antiparticle. If one has positive energy, the other has negative energy. Now, one member escapes the event horizon, the one with positive energy, and the other particle carries negative energy. It falls inside the black hole, which will decrease the mass of the black hole. So this explanation was suggested by Hawking, but this explanation was for virtual particles, which we cannot physically observe. And in Hawking radiation, photons are released. So was it not correct to conceptualize it with matter and antimatter particles? And most importantly, as we mentioned earlier in the case of Hawking radiation, it is not released from the black hole's event horizon, but rather from a larger area around it. But if you still want to go with this explanation, then you will have to think about 4 different conditions here, because there is no guarantee that the positive particle will always escape the event horizon and the negative particle will always go inside the black hole. So here, these 4 possible cases can be formed. Number 1, out-out pairs, in which neither of the particles will cross the black hole's event horizon and they will annihilate each other and disappear. In this, the particle escapes the event horizon and the antiparticle goes inside the black hole. In this, the particle falls into the black hole and the antiparticle escapes the event horizon. And number 4, in pairs, in this, both particles go inside the event horizon. Out of these 4 scenarios, there are only 2 conditions where a photon can be released, and that is through the interaction of in-out and out-in pairs. Now, the energy that is released from those particles in the form of photons has to come from somewhere. Now, it's not like a particle just came into existence from nothing and released energy, and that energy can't come directly from inside the black hole, because our understanding says that nothing can come out from inside a black hole. But there was a concept we saw at the beginning of the video, and that was that curvature and mass are directly connected to each other, and it's the curvature that links the black hole to the outside physical world. So this very concept is going to help us with this problem here. So that missing energy will come from the curvature of space, and as soon as the curvature decreases because some amount of energy has already left from it. In the same way, the mass of the central black hole will decrease, and through this very slow process, the entire black hole will eventually disappear. So this was Hawking's explanation, but even here, the radiation did not come out from inside the black hole. Rather, it is released from the particles forming outside the event horizon. And in exchange, the energy that was lost happened due to the curvature of space-time, and it reduced the mass of the black hole. However, not everyone liked this explanation, because no one knows how the space-time fabric works at the quantum level in highly curved regions, especially near a black hole. But quantum field theory has some answers to this. Calculations of quantum field theory in curved space have given us some very surprising results. That this thermal and blackbody radiation being emitted from the black hole's event horizon depends on the size of the event horizon. For example, the smaller the event horizon, the greater the curvature of space there, and the greater the curvature, the higher the rate of Hawking radiation. That means the rate of Hawking radiation will not always remain the same. For example, if there is a very large black hole, as time passes, its mass will decrease due to Hawking radiation and it will become smaller. As the black hole shrinks, its mass will decrease, and this process will become even slower, and eventually the black hole will evaporate. A black hole with a mass equal to our sun would take 10 to the power of 67 years to evaporate. The central black hole of the Milky Way will take 10 to the power of 87 years to evaporate, and the largest black hole in the universe will take 10 to the power of 103 years. By the time evaporation happens, every star in this universe will have died, particles will have moved infinitely far apart from each other, which means our entire universe will have died by then, and the whole universe will have lost its ability to form complex structures. Now, the last remaining energy will only be left in these black holes when the black holes reach their final stage. There will be a cosmic burst from one of these, which will be just like a Big Bang, and then finally, something will come out from inside the black hole. The light that is trapped inside it today will then try to illuminate this universe, which has turned into a graveyard. This Milky Way of ours is just a small part of our universe. Our galaxy is neither much smaller nor much bigger than the other galaxies seen in this universe. Our universe is so unique that there are galaxies found here that are millions and billions of times bigger than the Milky Way. And at the center of all these is what drives these giant galaxies, a supermassive black hole. Black holes, the masters of darkness, are one of the greatest mysteries of this endless universe. As far as we know about black holes, they have always been a center of attraction for all of us, the most mysterious and so immense that there is no need to even describe their power. These cosmic giants, often described as terrifying, remain hidden at the centers of galaxies. These unimaginably powerful giants have been visible to us in the history of the universe since the very beginning of its existence. Recently, scientists have found some evidence that suggests black holes. They existed in our early universe much earlier than we ever imagined. This discovery could change our understanding of the early universe. After all, what were these mysterious objects doing at the very beginning of the universe? How did they form so quickly, and how did their evolution happen in that early universe? Astronomers have long studied and still study the early universe. They were puzzled about the presence of quasars. Finding quasars in the early universe means that supermassive black holes existed there. And this conclusion surprised scientists even more. These observations have raised many questions. How could supermassive black holes possibly form in the early universe, which was not even a billion years old yet? There simply wasn't enough time in these observations. So were they born as unusually massive giants, or did they somehow learn to grow very quickly, breaking the rules of the universe? A study has been published in the astrophysical journal Letters using data from the Hubble Space Telescope. And this study revealed that the early black holes were less luminous and were growing in a universe filled with darkness. Because of this characteristic, they had managed to escape our observation until now. This astonishing discovery not only deepens this mystery even further, but it also provides us with a lot of new information about the formation of black holes. Let's go on a journey of black holes today and see how these black holes were forming in the early universe. Let's also take a look at what the James Webb Space Telescope has told us about black holes. So get ready to embark on an exciting journey filled with the mysteries of this universe. The mystery of early supermassive black holes is one of the biggest unsolved puzzles in science so far. How did supermassive black holes come into existence right after the Big Bang? Quasars, which are among the brightest objects in this universe, are powered by giant black holes. Scientists observed these quasars in galaxies present in the early universe when the age of the universe was not even 1 billion years. Now, these objects are such that in just 1 billion years, for them to grow so much that they become supermassive black holes and form quasars, it's just not possible. It's like if I ask you, have you ever seen a 10-year-old old man? You would say, brother, how can someone be born and become old in just 10 years? Scientists are also puzzled after seeing this exact same case. If they had so little time, then how did they grow up so quickly? When it comes to black holes, they grow by swallowing the gas, dust, and other things around them. All this matter falls into the area of the black hole's accretion disk, and from there, it slowly gets absorbed into the black hole. As this matter falls into the black hole, it collides with the other matter present in that accretion disk. Due to this, because of friction, it heats up, and that's why the matter present in the entire accretion disk reaches a very high temperature. This causes intense radiation to be released from the whole accretion disk, and this radiation creates a pressure barrier. And a limit is placed on the matter consumption of black holes, which directly affects the growth of black holes. Considering this limit, scientists are unable to explain how, despite this limit, black holes became so massive in such a short time during that period. The two possible solutions given by scientists are as follows. Either these giant black holes must have formed from stellar mass black holes, which are the remnants of a massive star. Those that die very quickly take less time to reach the stage of a supermassive black hole. But if this process speeds up a little, then they can grow within a given limited time. Now, because they start off with a mass 1,000 times heavier than our sun, that's why they're also called heavy seeds, and because of this, they quickly reach a large size. But where did these heavy seeds actually come from? One theory suggests dark matter halos. These are structures made of invisible matter that hold galaxies together. These structures are they also trap gas clouds in large quantities and prevent those clouds from turning into a star. When stars do not form from those gas clouds, they directly collapse into a black hole. This leads to the formation of a large heavy seed. However, the problem still remains. Only a few dark matter halos have been found to be large enough to trigger direct black hole collapse. Black holes formed in this way should be found in very small numbers in the early universe because the dark matter halos that create them were themselves quite rare. But a recent research has shown that the number of black holes we have observed in the early universe is much higher than our calculations. And because of this, astronomers are now forced to believe that some very mysterious forces were at work in the early universe, because of which our current science is not able to understand them. Now, how can there be black holes without any mystery surrounding them? Because of black holes and James Webb Space Telescope discoveries, thanks to advanced technology, astronomers are now able to find black holes hidden in galaxies present in the early universe. Earlier, we could only detect those bright quasars because they are very bright, but recently, observations from the Hubble Space Telescope have also discovered many faint black black holes that had remained hidden from us until now. Scientists monitored 15 years of brightness data from galaxies. This has enabled them to estimate the black holes that are quietly growing in the universe. This method has given us new data which shows that the number of black holes we previously assumed, in reality, their number in the early universe is many times higher. The James Webb Space Telescope has taken this discovery even further. Thanks to its extraordinary sensitivity and advanced spectroscopic capabilities, James Webb Space Telescope has also started detecting faint black holes in the early universe. It is closely monitoring their activities. This telescope is also capable of detecting the faint glow of black holes hidden within galaxies. This will help astronomers refine our early models of the cosmos. But then this raises another question. If so many black holes existed at that time, how did they all grow so quickly? After all, where did so much matter come from for them to consume? According to scientists, the answer to this might be hidden. In mealtime variability, unlike stars, black holes do not grow continuously. Their eating habits vary at different times. Instead, they keep a gap in their eating times. They take breaks. Because of this, it becomes difficult to estimate what the actual rate of their size increase is. Black holes deceive us here as well. This discovery is also groundbreaking because it contradicts our earlier models, meaning it proves the models we created to be wrong. Scientists now believe that all the black holes discovered so far, from the extremely bright quasars to the recently discovered less bright black holes, there are so many of them that they couldn't all have formed from direct collapse. This suggests that there must have been some extremely mysterious processes at work at that time, which were creating not only large but also a huge number of these black holes. In the next 5 years, the James Webb Space Telescope is going to play an important role in solving this cosmic puzzle. Its ability to observe faint black holes also gives scientists the power to witness the death of the earliest stars. And this event can tell us where the initial seeds of black holes came from in such large quantities and how the universe continued its journey forward. Apart from the standard theories of dark stars' black hole formation, scientists are now considering even more bizarre ideas to somehow explain the black holes of the early universe, and one of these is among the strangest ideas. The concept of dark stars, however, is completely hypothetical, meaning they are entirely imaginary. This star forms when a large cloud of gas starts to collapse, just like a normal star forms. But when dark matter is present during that normal star formation, something mysterious happens. As the gas present in the cloud contracts, meaning it shrinks. It captures dark matter particles in large quantities, and these particles modify the internal structure of the star that is about to form in such a way that the process of nuclear fusion at its core stops, which is what makes stars shine. Without the fusion process, this star cannot shine like a normal star. But it lives much longer than those stars and becomes extremely massive. And eventually, these stars collapse under their own weight and turn into a black hole, which is much larger than any normal stellar mass black hole. It's interesting to think that if these objects existed in our early universe, they could explain the observation of so many black holes that we see. However, dark stars are still a theoretical concept for us, an imaginary idea. But telescopes like James Webb Space Telescope can play an important role in proving the existence of such massive stars. Observing the collapse of those early stars with our telescope can tell us whether dark stars played a major role in black hole formation in the early universe or not. This adds another exciting possibility to the growing list of questions about these black holes. Are there some processes at work in the universe that we haven't fully understood yet? Future of black hole research, there is a very high possibility of such interesting discoveries in the future. In the past few years, there has been a new revolution in research in this field. Upcoming missions like the Euclid mission and the Nancy Grace Roman Space Telescope will help not only in observing faint black holes, but also in observing faint quasars. Meanwhile, observatories like the Square Kilometre Array or Square Kilometre Array being built in Australia and South Africa will help us understand black holes in greater depth, but for now, James Webb Space Telescope is at the forefront of this research. By observing some of of the faintest black holes in the early universe, it is helping us refine our old models. In the coming years, with its help, we will even be able to find a star in the process of forming, and that discovery will be historic. We are trying to learn about and understand our own history. But perhaps the universe is such that whenever we get close to understanding its origin, new questions arise before us along the way. Friends, what are your thoughts on this topic? Do let us know in the comments section. And if you like this video, please like it and share it with your friends. For more such informative videos, make sure to subscribe to the channel and turn on the bell notification. Friends, we'll meet again soon with another new informative video like this. Until then, stay curious, be happy, and goodbye.